Hello everyone, and welcome back to another video where we are going to be finding out what infinity factorial is. And when I say that, I really just mean finding out what the derivative of the zeta function is at 0. But the way we're going to do that is not as you might expect, because we are not going to start with the zeta function at all, or even with finding the derivative of any function at 0. We're going to start with the eta function right here and evaluate its derivative at 1, and then go from there to figure out what exactly zeta of 0 really is. So without further ado, let's get to it. So taking the derivative of this right here, the integral definition for the eta function, we can just use our good old product rule. And what we obtain is just going to be the following. So we know that eta prime is just going to be gamma prime of s right here, and then over gamma squared of some s, and the negative sign, of course, because, it's a 1 over. And then we have the integral from 0 to infinity of, well, x to the s minus 1 over e to the x plus 1 dx. And then just taking care of the integral term for the product rule, we have 1 over gamma of s, and then times the integral from 0 to infinity of x to the s minus 1 times the natural log of x, and then over e to the x plus 1, and then dx. Now taking the limit, or really just plugging in s equals 1 here, we find that, well, a lot of these things just go to 1. So in this first term right here, we plug in s equals 1, right? The denominator is just going to be 1, right? So we just have minus and then gamma prime of 1, but that's just defined to be the negative Euler-Mascheroni constant. So we really just have a positive Euler-Mascheroni constant, and then times the integral. 1 minus 1 is just 1, so from 0 to infinity of just 1 over e to the x plus 1 dx. And then we have plus the second term right here. The term out front is just going to be 1. And then we have the integral from 0 to infinity of just natural log of x, and then over e to the x plus 1 dx. Now, if you remember the previous video, we evaluated this exact integral right here. So we found that this right here was just equal to negative 1/2 of natural log squared of 2. We can evaluate this one right here pretty quickly, actually, because we find that its antiderivative is just going to be Euler-Mascheroni constant out front, obviously, because it is a constant. Natural log of 1 plus e to the minus x, and then evaluate that from 0 to infinity. The term at infinity is just going to go to 0, but if we plug in 0 into here, we end up getting the Euler-Mascheroni constant times the natural log of 2, and then chucking on that bit right there, we have minus 1/2 natural log squared of 2. And that right there is equal to eta prime of 1. So how exactly can we relate eta prime of 1 all the way to zeta of 0? Well, we have a couple of formulae for that. So one of the formulas we can use is this one right here. It's relating the eta function to zeta. So just eta equals, and then 1 minus 2 to the 1 minus s, and then times zeta of s. But we don't exactly want to employ this yet by differentiating both sides, namely because we know that zeta actually has a pole at s equals 1. And finding the derivative there and trying to get a number just gets very messy. So what we can do instead actually is, before using this formula right here, we can use a different one. And that one right there is a eta reflection formula, which is, well, just this right here. So we have eta of negative s is equal to 2s, and then times the sine of pi s on 2. I'll probably do a video proving this at some point. And then gamma of s, and then times 1 minus 2 to the minus s minus 1 over 1 minus 2 to the minus s, and then times pi to the minus s minus 1. This is a mouthful, I know. And then eta of s plus 1. Now, how on earth can we use this formula right here? Well, you'll notice that if we plug in s equals 0 right here, we get an eta of s term, and then an eta of 1 term, and then an eta of 0 term. So we can actually use this to figure out what eta of eta prime of 0 is, and then once we know what eta prime of 0 is, we can figure out what zeta prime of 0 is. So before we actually go differentiating, let's note a couple of things. Whenever we plug in, or take the limit, really, because there are poles, whenever we take the limit as s goes to 0 in this formula right here, well, you're going to get a 0 over 0 in multiple ways, actually, because you see that we have, well, that's a pole, but that's going to cancel it out. We have another pole right here, but then that's going to cancel it out. So because we have two of those, and I don't feel like applying L'Hopital's rule about 20 different times, what I'm going to do actually is do a little approximation, which I typically don't like in videos, but in this case it works out perfectly well, because if we express all of these in terms of just Taylor series or Laurent series, what we can do whenever we take the limit is just all the higher order terms are just going to drop out anyways, even when we differentiate. So if we just include the first two terms of each Taylor / Laurent series, and we find the limit as s goes to 0, we're going to end up with the exact same result. So let's go ahead and express some of these as Taylor / Laurent series. So let's just go left to right to get started. So we see that we have this sign right here. I'll deal with the gamma in a moment in this S. But the sign right here, well, what's our favorite engineering joke? It's that sine of x is equal to x. So we can just approximate this, right, as just pi s on 2, which is just going to cancel with this 2 right here. So I'm going to add an approximately equal to side right there. So it's going to be pi s on 2, but we can just write that as pi times s. Okay, so that's one term down, one check mark. What about this gamma term? Well, s times gamma of s is just gamma of s plus 1. So we have, let's see, gamma of s plus 1. But one way we can approximate that is actually by just 1 minus times the Euler-Mascheroni constant, and then just times s right here. You can actually derive this from the fact that gamma of, well, 1 is just 1, and that the derivative of the gamma function at 1 is just the negative Euler-Mascheroni constant. So that's where that comes from. And then let's focus on this term right here. I'll save the best for last right there. This pi term, again, it's actually really simple. If you just expand that out in terms of the exponential, what we end up getting is just a 1 minus natural log of pi. Keep your eye on that natural log of pi. That's very important. And then just times x. And then we have this right here. Now this term right here is a very peculiar one, namely because in order to express it, we're going to have to use a Laurent series. And I'm not going to prove this in this video because, well, the first term is actually really easy to derive, but the second term involves calculating a very, just a bad residue that I don't want to deal with. It just gets very messy very fast. So please take my word for it. I'll leave this as an exercise to the viewer, I suppose. But what this is right here is just going to be 1 over, I realize I'm mixing up x's and s's now. Whoopsies. That should be an s. Okay, what we have then is just going to be s. I'll put parentheses here so you know the difference between terms. So s times natural log of 2, and there's a specific reason why I'm writing it like this, and then 1/2, and then plus 3/4 s natural log of 2. Okay, and then of course times our eta function right here, so just eta of s plus 1. Okay, so what happens when we differentiate all of this right here? Well, before we do, we can actually see that two of these terms cancel. We have this s right here and this s right here. Those just cancel. So, okay, and I do apologize. Whenever I wrote this right here, so this term, I did include this pi, so this pi is just redundant. Apologies for that. So let me just clean this up real fast. So get rid of that and then get rid of that. And okay, this is the actual formula we're going to be differentiating. So what happens when we actually do differentiate this? Well, we can just do this term by term because it's just going to be one big product rule here. Let's just start with our eta term right here. And again, we're differentiating and then plugging in s equals 0. So we have eta prime of 1. So eta prime of just 1 right here. And then times, we're going to plug in 0 for everything else, right, for all the other s's. For the gamma term, we just have a 1, same thing for the pi term. And then for this term right here, this is the only one that's not going to be 0, and that's because it's just going to be 1 over 2 natural log 2. So I'm going to write it in a different color, 1 over 2 times natural log of 2. Okay, so now we're going to have a plus, and then for the sake of just making things look a bit nicer, I'm going to throw in an eta of 1 right here. So this is a normal eta of 1 right here. And we're going to just apply product rule to the remaining 3 terms, right? So just starting with, you start with this one right here. If we differentiate it, then we end up with just a 3/4 times natural log of 2, which just gives us, whenever we include the 1 over natural log 2, which literally just gives us 3/4, right? So we have 3/4. And then the other 2 terms are just going to give us just 1. So, okay, cool. We have a 3/4 right there. And then next, we're going to differentiate this term right here. So then we have minus natural log of pi. So we have minus natural log of pi times 1, of course. We plug in 0 into this, and we end up having a 1 over natural log of 2, and then a 1/2. So 2 natural log 2. And then finally, when we differentiate this term right here, we're going to have just a minus gamma. So yeah, it is a gamma, but minus Euler-Mascheroni constant. I shouldn't say gamma because that might refer to something else. But we have minus Euler-Mascheroni constant, and then times, well, 1, and then times, well, as we've already established right here, plugging to 0 into there, we have a 1 over 2 natural log 2 right there. Okay. So you might be wondering, actually, what exactly is eta of 1? Well, eta of 1 is actually just the alternating harmonic series, which is a fun little fact right there. Eta of 1 is just the natural log of 2. So we can distribute all this right here. So we can so get rid of that, natural log of 2, and then that's going to cancel, and that's going to cancel right there. So let's go ahead and expand out everything right here. So let's go ahead and drop in what we found for eta prime of 1 right here. So eta prime of 1, as we already said, just throwing out this term right here, was just Euler-Mascheroni constant times the natural log of 2, and then minus 1/2 natural log squared of 2. Okay, and then we're going to have plus all this other stuff. So we're going to have plus 3/4 natural log of 2, and then minus the natural log of pi on 2, and then minus Euler-Mascheroni constant on 2. So let's go ahead and distribute this right here and see what we get. Well, we get a Euler-Mascheroni constant on 2, and then a minus 1/4 natural log of 2. And you'll see that a couple of these terms actually cancel, namely this one right here with this one right here, and this one right here cancels with this right here, so long as you just make this like a half, right? So we can absorb that just into one term. So what we end up getting in total is that eta prime of 0 right here, or really negative eta prime of 0, because this was eta of negative s to begin with. So negative eta prime of 0 is just equal to natural log of 2 over 2, and then minus the natural log of pi on 2. And then just throwing in the minus sign here, right? So we have the actual derivative of the eta function of 0. It's just this right here, which we can conveniently rewrite as 1/2 times the natural log of pi on 2. Okay, so now that we have that, we can make use of one of our earlier formulas that I mentioned. This whole eta of s thing equals 1 minus 2 to the 1 minus s, and then times zeta of s right here. So differentiating this according to product rule, we have eta prime of 0 is going to be equal to, well, the derivative of this first term. So that right there is just going to be 2 to the 1 minus s times the natural log of 2, and then times zeta of 0. And then we're going to have just plus 1 minus 2 to the 1 minus s, and then zeta prime of 0 right there. Now, plugging in s equals 0, what we find is that, well, we have a 2 up front here, and then we have a natural log 2, of course, but zeta of 0 is actually just negative 1/2, which will cancel with this 2, so we can just add a negative here, according to that. And then we have our plus. Well, this plus actually isn't really a plus, is it? Because we have a 1 minus 2, and 1 minus 2 is just negative 1. So really, that right there is just going to be minus, and then zeta prime of 0. And now, of course, this is equal to eta prime of 0, and we know that to be 1/2 natural log of pi over 2. We just derived that. So let's go ahead and solve for this zeta prime of 0. We can just add and subtract from both sides of the equation, and what we end up getting is zeta prime of 0 is just equal to negative 1/2 times the natural log of pi over 2. So just that eta term, and then just minus the natural log of 2 right here. But it'd be awfully nice if we could get these logarithms into a single logarithm, right? Just using properties of logs. So let's just go ahead and add a 2 here and divide by 2 here. But by properties of logs again, we can just combine these two together, right? So that's going to be 2 raised to the 2 power. So erasing that, we can end up with a 4 right here. So what that means, factoring out a negative 1/2, is that this right here is equal to just negative 1/2 times the natural log of 2 pi. And that right there, ladies and gentlemen, is just going to be zeta prime of 0. Now, how exactly can we get infinity factorial from this, though? Well, let's go ahead and look at the series definition of the zeta function. So zeta is defined as a series like this. It's just the sum from k equals 1 to infinity of k to the minus s. And if we go ahead and actually just differentiate that and plug in 0, what we end up with is just going to be negative k, or the sum from k equals 1 to infinity of just the natural log of k. But what's another thing we know about logarithms? Well, if we add 2 logs together, or 3 or 4 or infinity, we can just convert that into a single logarithm, right? So what we can say is this right here is equal to the negative natural log of the product from k equals 1 all the way up to infinity of just k. But this right here, this product from 1 to infinity of just k, that's another way to think of the factorial, sort of, for finite numbers at least, right? And for integers. It's like 5 factorial is just 5 times 4 times 3 times 2 times 1. That's obviously what this is. So in a way, kind of sarcastically, this is infinity factorial, sort of. And just comparing notes right here and including this 1/2 into the logarithm, we can sort of see, in conclusion, that infinity factorial right here, in quotation marks, equals the square root of 2 pi. And that right there is our result from today. I hope you all enjoyed this video. And I'll catch you in the next one. Thanks for watching.